Welcome back, everyone. We'll now like to introduce our next speaker. His name is Gunnar Grosch. He'll be talking about how to do chaos engineering in the serverless world. I'll let you take it from here, Gunnar.
One and all, and welcome to Performing Chaos in a Serverless World. I am Gunnar Grosch, and I am really excited to, if not see you, at least know that you're out there. So this is the abstract of this talk, and hopefully what brought you here today. So the principles of chaos engineering has been battle tested for years, using traditional infrastructure and containerized microservices. But how do they work with serverless functions and managed services? So the agenda for this talk is we'll cover what chaos engineering is, some of the motivations behind chaos engineering. We'll look at how to perform chaos experiments. In short, what serverless is, the challenges with serverless, and what some of the common weaknesses are that we can test for in our applications. And of course, we'll finish it off by doing some experiments. So I did a talk at reInvent in December, and someone wrote in the feedback that I should talk less about myself and more on the subject. So as soon as I stopped crying, I decided to keep this pretty short. So I'm an evangelist at Opsio, based in Sweden. I have a long background in tech. I enjoy building technical communities. And I have been named a serverless hero by AWS. And I am divorced. I have 3 kids. So chaos engineering was quite a natural choice for me. So let's get to it. What is chaos engineering? Chaos engineering is not about breaking things. We often hear that we should break things on purpose, and it's nothing wrong with saying that. I'm all for bringing attention to the practice, so I don't really mind using that phrase. But as long as we all agree on that breaking things isn't the purpose. Sure, we do break things. We break things pretty often, but the breaking part isn't the purpose. Learning is the purpose. Chaos engineering is not only for production. We often hear that chaos engineering should be used in production, and hearing this can be an obstacle for anyone trying to introduce chaos engineering in their organization. Sure, we want to do it as close to production as possible. And you can do experiments in test, in dev, in staging, in a playground environment. The more production-like, the better. But think about replaying traffic, using it with load testing and so on, if you're unable to do it in production yet. There are a bunch of companies doing chaos engineering successfully without doing it in production. And chaos engineering is not only for the big streaming companies. You don't have to be Netflix to do chaos engineering. You don't even have to be like Netflix. Data shows that more and more companies are hiring chaos engineers or site reliability engineers with the responsibility to do chaos engineering. And chaos engineering is today used by companies ranging from e-commerce to fintech and banking, as well as smaller startups committed to being reliable. And you can't really have a chaos engineering presentation without showing this slide. Principlesofchaos.org is a website released alongside the first book on chaos engineering. So chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And reading this shows that it's less about doing things that are chaotic and more about experimenting. The chaos part of chaos engineering is more about what's inherent in the system. There is chaos in every system. So let's break that down a bit. Chaos engineering is about performing controlled experiments to inject failure. Doing experiments makes it sound quite scientific, and to be honest, it is. we create controlled experiments and we measure the results. So some compare it to a vaccine in that we inject failure into a system to make it stronger. And talking about it as a vaccine these days is really something that resonates. And chaos engineering is about finding the weaknesses in a system and fixing them before they break. So no matter how much we focus on making our systems resilient to failure, there's always unknown factors that come into play. We have traffic patterns, we have third-party dependencies, network issues, code deploys, configuration changes. And by doing our experiments and measuring the result, we can draw out these weak points in the system. And finding and fixing these can help you avoid that big outage that we all know never happens at the right time. And chaos engineering is about building confidence in your system and in your organization. By finding weaknesses and doing controlled experiments, we can build confidence in our system and how it works. But we also build confidence in our organization. The people are key in building resilient systems. And by building confidence, we gain trust. So perform experiments and you will learn new things about your application and most likely also about your organization. So let's look at some of the motivations for doing chaos experiments. And I think you all know this quote, and you all know Werner Vogel's, everything fails all the time. And Werner should know. Many of you probably remember the big S3 outage in 2017 and the effect that had on the entire internet. But there are failures and outages all the time. Verizon had a routing issue that affected a big chunk of major website. Cloudflare did a software deploy that affected them and everyone using them worldwide. Hey, even Netflix has outages. So, let's look at some of the motivations. Everyone that builds a system or runs a system has customers, be it internal or external customers. And are your customers getting the experience they should, or are your users unhappy? And we often say that nothing is free on the internet. So no matter if you run an e-commerce site, an ad-driven blog, or a SaaS solution, downtime or issues probably costs you money somehow. And what happens when the incident is there? Are you confident in that your monitoring and alerting will actually notice? Will the on-call get that page needed to start engaging with the incident? And you probably all have your runbooks and playbooks describing how to act when incidents and outages occur. But is your organization ready to handle these outages? And hopefully you do fire drills so that everyone knows how to act in case of fire in your building. But are you doing fire drills for incidents? And every time there is an incident, we have a huge opportunity to learn about the conditions that exist for that incident to take place. And what about learning from controlled incidents? By using chaos engineering, we're able to do that. So that brings us to, for me, the greatest motivation behind chaos engineering. Don't ask what happens if a system fails, but ask what happens when it fails. A resilient system isn't one that doesn't fail, but one that maintains an acceptable level of service in the face of failure. What happens when the system fails? Well, chaos engineering helps us reveal that. So, having said what chaos engineering is and why we want to do it, let's briefly look at how to run chaos experiments. And we'll do that by following some simple steps. First off, we define what's called the steady state. And without knowing the steady state, we can't really observe what happens when running the experiment. Steady state is basically the normal behavior of a system over time. Its highs, its lows, and its ups and its downs. So we use system metrics, or even better, business metrics like number of purchases, active users, and so on, to find the steady state. Next, we form our hypothesis. And an hypothesis is a proposed explanation made based on limited evidence as a starting point for our investigation. And we use what ifs to find it. What if the primary database goes down? We're using the scientific method of if-then to put our hypothesis together. If this, then that. If the primary database goes down, then we switch to the fallback database. With our hypothesis formed, we're now ready to plan the experiment and then run it. We should start out with the smallest possible experiment. So we contain what's called a blast radius. We start small and then we grow with confidence. And a blast radius might be the number of users affected, certain countries, and so on. And when we do our experiment, we make sure to have a stop button ready. So we don't want an experiment that grows or cascades. So having a way of stopping it is really important. Next, we've run our experiment, and now it's time to look at the results. So you remember the first step when I talked about steady state? Those metrics will now help us to prove or disprove our hypothesis. So we, in a controlled fashion, injected failure of some sort. Was the system robust enough or adjustable enough to handle that failure injection? We took down the primary database for 5% of users. Did they switch to the fallback? And we've now seen what happened with the blast radius we set earlier. So with the confidence we've gained, we can now adjust the scope and scale up our experiments. So let's include more users, more hosts, other countries, and so on. And we'll probably see new effects then. And when you do your experiment, you'll probably end up with action items, bug reports, and so on, just like with a regular incident. And this is the part where we learn from incidents. It's just that this is the incident that never happened. So now we know how to run chaos experiments, and it's pretty straightforward, right? And this brings us to the serverless part. So in short, let's look at what serverless is. The AWS definition of serverless states that serverless allows you to build and run applications and services without thinking about servers. And this is not so much about the actual servers as it is about what running servers mean. It's about letting someone else do the long time work that is involved with running servers, and it lets you focus on maximum business value. And serverless isn't only about functions as a service, like Lambda, but the serverless landscape today consists of many, many different services that are used together to build a serverless application. So with serverless, we have no server management. There is no need to provision or maintain any servers. There is no software or runtimes to install, maintain, or administrate. We have flexible scaling in that your application can be scaled automatically from 0 to the highest peaks, or by adjusting its capacity units rather than the number of individual servers or instances. We pay for value in that we pay for the consistent throughput or the execution duration rather than by server units. And we have automated high availability. Serverless provides built-in availability and fault tolerance. So you shouldn't need to architect specifically for these capabilities since the services running the application provide them by default. And Paul Johnston is an advisor to startups and is well known in the serverless community for his thought leadership. And in his latest definition of serverless, and there has been a few through the years, he states that serverless is not a technology, it's a mindset. The point with that being that we shouldn't focus too much on the technology because then we'll miss what's coming next. Again, we use serverless to provide maximum business value. So With serverless, we have some challenges though, and that's what we're going to look at right now. If you ever talked serverless with an old server hugger, you've probably heard this line: there are still servers in serverless. And there are. The thing is just that we don't manage them. And that leads us to some of these challenges. So we don't have any servers to manage. And that means that we have potential sources of failure that we don't or can't control. The failure modes for the underlying infrastructure is quite unknown. Less heavy lifting. I'm all for less infrastructure work. We just need to remember that every time someone sets up or configures infrastructure, they usually learn a lot about how it works. They find sources of failure and are aware of them. Once again, things in serverless are unknown for us. And besides serverless functions as the most common part of our architectures, we have a vast amount of services to choose from. Databases, key value stores, notification services, queue services, object storage, and so on. Everyone with its own potential sources of failure and unknown failure modes. And for each function and for each service we use in a serverless application, we have separate configurations and security policies. And this is great for control, but to be honest, it also gives us opportunity to introduce failure in our application. Our applications, our serverless applications, are usually more granular in that they contain lots of functions, lots of services, and interconnections. All in all, we have more inherent chaos. And remember that serverless doesn't make your application resilient. The people who build it do. In my opinion, chaos engineering is a perfect fit for serverless. And what I mean by that is that serverless, with its inherent chaos and granular architectures, is well suited for chaos engineering. Use chaos engineering to help build more reliable and resilient applications. And you can start by nothing more than the cloud provider's CLI needed as a tool. And serverless applications are distributed systems by default, and using chaos engineering can help us verify that things work as intended. So, designing chaos experiments for serverless forces us to think a bit different, since we don't have any EC2 instances to shut down, any pods to destroy, or network interfaces to mess with. So, we can start by looking at some of the common serverless weaknesses seen in architectures. Are we handling errors correctly in our application? No matter if the error handling is inside our code or a feature in the service, we'd better make sure that we're handling them properly. Releases like SNS dead letter queues or Lambda destinations and others are great where the cloud provider takes the load of error handling. But I, for one, want to make sure that it works. With serverless functions and dependencies in the form of other managed services or third parties, we need to and want to get our timeout values right. They are probably in most cases correct when in steady state, but what happens when there are issues, say latency? And with event-driven architectures becoming more and more common, how we handle events is key. Are we queuing them correctly? What happens to events in case of service failures? And using many services and third-party dependencies means that we trust them to be there. Do we have fallbacks? Do we have graceful degradation when they're not there? And I don't want to jinx us, but regional outages rarely happen. But having regional failover or using multi-region is of course not only for regional outages. What if a major ISP have issues affecting traffic to your region? And these are just some potential weaknesses, and there are, of course, a lot of others as well. And if you want to learn more about how to fail with serverless, and not just that you can fail with serverless, you should check out Jeremy Daly's talk that is later tonight. Okay, so let's look at some practical serverless chaos experiments we can do. This is a simple architecture, a web service using an API with a couple of Lambda functions using DynamoDB and objects stored in S3. And we can then inject errors into our code or create exceptions in our code to see how our application handles that. We can remove downstream services, in this case DynamoDB or S3. And we can, of course, alter the concurrency of functions or restrict the capacity of tables to see how that affects our application. As I mentioned earlier, we have configurations and security policies for each and every small part of our serverless applications. And we can use that to inject failure and then still be within the small blast radius in mind. We can also inject function disk space failure, because even though we're running this as functions, there is still a disk that might be in use in your application. Or we can use the mother of all serverless chaos experiments, latency. And by adding latency to functions, we're able to create a bunch of different failure scenarios, like cold starts that might affect functions if they haven't run for a while, different cloud provider issues, runtime or code issues, integration issues with downstream, upstream services, or to check our timeouts to make sure that our timeouts is working as intended. There are some tools that can help you to do chaos experiments for serverless. Our host tonight, Gremlin, has their application layer fault injection. Still a bit limited, but I do believe there is more support coming. We have the open source Chaos Toolkit, which has support for different serverless services. The observability tool Tundra has a built-in support for failure injection into the serverless application that you are monitoring. Adrian Hornsby of AWS, he built a Python library called Chaos Lambda that allows you to inject failure into your Python Lambda functions. And then we have the Node.js libraries that I've built for Lambda, Azure functions, and for cloud functions. So on to the practical part, and let's do some experiments. This is what's called serverless chaos demo site. And I built this as a way of showing how we can do chaos experiments on serverless. And that's what we'll be using tonight. And this is the architecture. It's quite similar to the one we saw earlier. We have an API gateway. We have some Lambda functions fetching data from a DynamoDB table and an S3 bucket for object storage. And we'll be using the Failure Lambda NPM package for our experiments. And it works by wrapping the Lambda function handler, and then we do configuration through parameters. And we have a few failure modes to choose from with, for example, latency, exception injection, and blacklisting. So with that, let's imagine that we have our steady state set and we know how the application normally behaves. So let's create a simplified hypothesis. What if my function takes an extra 300 milliseconds for each invocation? What if my function returns an error code? What if I can't get data from DynamoDB? And the hypothesis here is that if we inject failure to functions, then my application will use graceful degradation. Let's go on to the demo. So this, Okay, now it's running. So this is the serverless chaos demo site. As we saw in the architecture diagram, it has 3 Lambda functions being invoked every 5 seconds, fetching a random URL from a DynamoDB table and loading an image from S3 object storage. Every invocation is 200 to 300 milliseconds. The 3 Lambda functions have the failure Lambda npm package installed, and through that gets their configuration. And it is in a parameter each in Systems Manager parameter store. So let's look at the parameter for function 1. So the configuration is done through JSON, and we can see that it is disabled right now. This Lambda function has its failure mode set to latency injection and with a rate of 1, meaning that it will inject failure on each invocation. It will inject a minimum of 100 milliseconds and a maximum of 400 milliseconds. So let's enable it and see what happens to function 1. So as we can see, the function is still working and new images are being fetched. But looking at the invocation time, we can see that it, as intended, takes somewhere between 100 and 400 milliseconds longer for each invocation. So by doing this, we're able to simulate different failures involving latency. So let's move on to function number 2. So this is the configuration for function 2, disabled for now and with the failure mode set to status code. With that, we're able to inject a specific status code. In this case, we're using 404 instead of the normal 200 you would get from a successful request. We can also see that the rate is set to 0.5, meaning that failure will be injected on roughly half of the invocations. So let's enable failure injection on function 2. And now we can see that function 2 is returning status 404 and not loading new images on about every other invocation and 200 on the rest. By injecting failure this way, we can verify that our application handles status and error codes in the way we intended. And finally, function number 3. Function 3 has its failure mode set to blacklist. And in this case, we're blacklisting calls to S3 and to DynamoDB. But it could, of course, be any service or third party in use. So let's enable blacklisting on function number 3. And as we can see on function 3, it has now gone from loading new images every 5 seconds to not loading images and giving an error instead by blocking connection to DynamoDB and simulating a service outage. So this was an example of how we can quite easily inject failure into functions in our serverless applications by adding latency, manipulating status codes, and blacklisting connections to downstream services. So, to recap, everything fails all the time. And serverless in itself doesn't make your application resilient. You, the builder, the architect, the operator, makes the application resilient. And chaos engineering helps us find weaknesses and fix them. And chaos engineering is about building confidence. Confidence in your system and confidence in your organization. And for me, chaos engineering is a perfect fit for serverless. And remember that it's not rocket science. You can do it. You can start using chaos engineering. Bunch of resources if you want more. I'll post all of them in the Slack channel for you to use. And with that, thank you all very much.